This meeting is being recorded.
Okay. Today, we are going to be talking about, we are in the topic 9 folder here. We will be talking about Mvcc, which is multi-version concurrency control, which is the technique that Postgres uses internally for implementing these atomic and isolated transactions. The reason that we are talking about this after talking about the transactions and locks stuff is because this material doesn't really help us understand like why we would want to use transactions and locks or how they behave. This is all fully internal to Postgres, and it's the sort of material that has relatively little observable behavior to the end user. And in particular, for only thinking about correctness behavior, you don't need to understand anything at all about the Mvcc here at all. Whether a program is correct or not, whether it deadlocks or not, whether it blocks in certain situations, whether data ultimately gets inserted has no bearing on this implementation detail stuff here. But how this implementation material does affect us is that we need to understand it in order to make our select queries fast. So I've been talking all semester about we're eventually going to make our select queries fast. And after this topic, we will be able to do it. There will be a lot of material here. And so we will see that one does not simply update a database, but maybe fortunately, maybe not fortunately, you're not going to be directly quizzed on the material from today. Instead, it's going to come up in next week quiz on indexes. And if you don't understand this material, it will make understanding the indexes, which is the technique for making SQL queries fast, much more weird and difficult, and it'll not click why the indexes behave the way they do in different situations. So that's what our outline of today is. There's no, again, direct quiz on this material, but it will be important for the upcoming topics. You do have the quiz on Thursday, next class period, on the last of our transactions locks quizzes. And there was no lab from last week, no separate lab assignment, but there was the homework assignment that we started in the lab time, and you have until next Tuesday, a week from today, to complete it. Shouldn't be hopefully too hard of a homework, but you do have the extra time. There are a lot of small weird things that can come up in that homework assignment that many of you observed in the lab period, but the actual assignment itself, once those small things are ironed out, not too long or too difficult. Any questions about anything administrative or non-administrative before we get started here? Maybe one last preamble that I will say is that previous semesters in this class, I have had oral exams for the class. I'm not doing that this semester because, well, many reasons, but the important ones are that I just like experimenting with class design to see what are different techniques that are going to be useful for students. And this material right here is the main part of the oral exam, that instead of spending I'm hoping we're going to get through all this material in one day. Instead of spending just one day on this material, we spent about 2 weeks on it, and this was the main part of the final exam. The reason this had to be an oral exam is because there's just not a way to test this material other than me asking like direct questions about it. And so this material very, very commonly not taught in undergraduate courses or any courses at any level. It's the sort of material that just experienced data engineers pick up as they go along. This is the sort of, the job description here would be data engineers or the people who are directly dealing with this material. Older job description names would be like database assistant, DBA. But we're going a little bit faster over this. Again, no final exam in this class, so we'll have a little bit more time at the end of the course to talk about various types of indexes and making them fast. Okay, the reference here that we'll be taking a look at, there's this textbook, The Internals of Postgres. This is written by a guy in Japan who is very, I don't know if he's actually super sensitive about his privacy or not, but there are no pictures of him on the internet anywhere. So I can't show you all a picture of him, but he's a famous guy in the Japanese, well, actually broader than Japanese in the Postgres world. This textbook, Internals of Postgres, is the standard book for understanding actually how Postgres works internally. And again, we will be talking about Mvcc here in the context of Postgres. Every modern database implements transactions using Mvcc, so SQLite and MySQL in particular. And some of the details will be slightly different, but yeah. So we'll be focusing on those parts of the details from Postgres here, but the big picture idea is all the same. Okay. This is what the textbook webpage looks like. If you haven't observed, there's a lot of elephants in Postgres. Elephants, the official motto of Postgres. And there's a bunch of pictures here that we're going to be going over in this textbook today. Okay. The first one here is this sort of background picture. And it's just showing the overview of what they call it the logical structure of a database cluster. Anytime you see people talking about logical, anytime you see the adjective logical come up in computer science, it means that they're not talking about the physical implementation in any way, anything underlying how bits are actually stored in the hard drive somewhere. But logical just means this is what is presented to the user. And the important keyword here that I just want to emphasize is that people talk about Postgres databases or MySQL databases or SQLite databases. When they do that, the more technical term is a database cluster. The word cluster here is unrelated to like a cluster in parallel programming, like multiple computers. It just means that there are these individual databases inside of one running database. Back before Docker, it was very common to have many different individual databases inside of a single Postgres instance. And after Docker, it's more common to just have one of these internal databases inside of a database cluster. So all of the databases that we've seen, you've had one just database inside the database cluster. And that's the standard way to do things. But Postgres does support having totally separate databases inside of it. And so inside the documentation in various places, you'll see the words database cluster, and that doesn't refer to anything about parallel computing. That just means database by itself. Okay. There's going to be a lot of things today where I am just talking, explaining various pictures, and if you do have questions, please feel free to interrupt and ask those. This is relatively uninteresting. The first super important picture here is this one. This illustrates how Postgres is physically going to be storing our rows inside of our tables on the hard drive. And again, this is the type of picture you need to be able to have in your head, conjure up into your head when we're talking about indexes so that we can understand why indexes are going to behave the way they are and why they're going to have certain limitations about them. On the left-hand side in green here, this table file is the file that actually stores information inside of a particular table in Postgres. In SQLite, we had just one file for the entire database cluster. In Postgres, we have one file per table. So the stored actually on the hard drive, there could be thousands of individual files containing your database information. These table files are divided up into pages of size 8 kilobytes. So 8192 is 8 kilobytes. And as we add more data, if we need to create a new page, it will just append a new page here down to the end. So we have 0 down to the nth page right here. And the size of this table is always going to be a multiple of 8192 here. Each one of these pages is formatted according to this part of the picture over here. Everything in blue here at the top is header information. There are conveniently 23 bytes of header information in the page, just like in the tuples themselves. And the actual data is stored from the end of the page towards the beginning. So this tuple 1 right here, this is the first row of information stored in this page up here. And again, tuples are synonymous with rows in the database world. The word tuple is the more formal word. It was the original word, and then the word row came up as a less formal synonym for tuple. But anytime you see tuple, you can think row. It's the exact same thing. And so there's a bunch of header information up here. The two, at least at this point, most relevant of these are the line pointers right here. This line pointer 1 and 2 point to where in the 8 kilobytes of space over here, the information is actually going to be stored for those particular rows. We've seen that these tuples can vary in size depending on whether they have null values or not inside of them, or depending on if you have a variable sized column. And so we need these line pointers right here to tell us physically actually where in this page that data is stored. This white spot up here, this white spot is called what it is it's free space. This is bytes that are stored on the hard drive that are not actually taking up space, not actually storing data or metadata. And this is commonly called the hole in the Postgres documentation. And again, when we're talking about indexes, how do we make our queries fast? We're going to need to understand this structure here of the page in order to see how the indexes are going to be able to find the data for us efficiently. One takeaway from this is that there's going to be a lot of wasted space, a lot of overhead here, because say in order to just store these two tuples right here, maybe these two tuples have only 10 bytes each. That would be a reasonably sized for a row, plus the 23 bytes of overhead. There's still has to fit inside of a 8192 bytes page, and so the hole over here will be fairly large. The actual header info up here, blue overhead, not too large. Again, only the 23 bytes, plus we'll have 1 byte here for each of these line pointers. But this hole over here is typically going to be fairly large. And so there'll be a lot of overhead. Any questions so far? Okay. This next picture here walks through how to actually add tuples to the table or to the page. How to add rows to the table is adding tuples to the page. And what it's going to do, there are these two pieces of header information, this PD lower and PD upper, which shows the start and end position of the hole inside of the page. And we'll have to update that PD lower and then add a new value right here, a new one of these line pointers. The line pointer points to where the new information will be stored for tuple 2 down here. And we'll update this PD lower to, it used to be showing right here at position 1. Now it gets moved over to position 2. PD upper shows the upper end of the hole. PD upper right here used to point to the start of tuple 1. Now PD upper will point to the start of tuple 2. One more picture over here shows at a high level what we're building up to here is that there are going to be multiple algorithms that Postgres can use to actually access information inside of the database and get it out to us. Two of the simplest are the sequential scan and the index scan. The sequential scan is what all of our queries so far have been doing. It's just basically a for loop over all of the rows in our data. And the way at a lower level that's going to work is it's going to go through each individual page, and then it's going to check each of these individual line pointers. After it visits the line pointer, it's going to find that particular tuple information and check if we satisfy whatever condition we're looking for. So it'll be going looping over like this. The index scan, however, will be a potentially more efficient method of finding information in these tables. And here we'll have a special data structure called this index, which will store these tuple IDs inside of it. A tuple ID is a page number combined together with one of these line pointers. So this particular tuple right here has a tuple ID of 7,2, the 7 for the page number and the 2 for the tuple number. So this TID right here refers to the TID is tuple ID, and block 7, the block is a synonym for page. Offset 2 is which of these line pointers we're looking at. And so we're going to have to, when we're talking about these indexes, understanding what these indexes are doing, we're going to have to understand how the information is stored in these pages down here in order to access it. Sometimes, I don't think I've used this word yet, sometimes these pages are called heap pages or heap tables. It's unrelated to the heap data structure, but it is related to the heap in C. If you're familiar with that, that's where the name comes from. But yeah, so I will sometimes use the word heap page to talk to about one of these pages that actually stores information inside of it. Okay, I'm going to keep pressing on if there's no questions. I realize this is sort of. So the two scanning techniques here, sequential scan is the for loop, and then index scan is the more efficient one that we'll go over in detail next week. And there's going to be actually 3 different variations of this index scan that we'll talk about. But these index scans are going to be the algorithms that we're going to try to use in most situations, or we're going to try to convince Postgres to use. Okay. So in order to talk a little bit more about, well, let's see. So this is the high level about what's going to go on in, like, physically in the hard drive. And this mostly should make sense, that it's maybe not obvious that this is the best way to do things, but it should be reasonable that this is a way to do things and store data in a way that you might be able to look it up efficiently. The next section here that we're going to talk about is chapter 5 in this textbook on actually handling concurrency. And so it's the concurrency control portion of this book. And what we're going to see is that there are a lot of weird edge cases, weird things that are going to happen in this model right here in order to handle our transactions. And that's going to complicate how we make our queries efficient. So first, as a reminder, so this picture right here is the structure of an individual tuple. We've talked about the user data section of this tuple. This is what we had to calculate on our quiz. I think it was just after spring break, so like 3 or 4 weeks ago. And we talked about this null bitmap, how the null bitmap allows Postgres to compress the user data section, because if a particular value is null, we don't need to store any user data over here. And then we had this 23 bytes of row overhead. And we're going to talk now about what goes on in those 23 bytes of row overhead. This is that heap tuple header data structure. 4 of these fields are particularly important for us. This txmin, txmax, tcid, and tctid fields right over here. Each one of these is 4 bytes long, and so this is 16 of those 23 bytes right here. All of this stuff in blue is related to information about transactions, and all of this stuff in white over here is just other miscellaneous information. Okay, so what happens when we actually do an insertion? Postgres will physically write this. So when we have, say, a transaction over here, we have this insert command, insert into table values A. Postgres will physically write values to the hard drive. And the user data section over here is exactly what we would expect from what we've seen so far, talking about the size of the data that gets inserted. And then over here in these right fields, this is what we need to talk about right now. These these left foremost fields, again, how transaction information is stored. And here we see the TXID. TXID stands for the transaction ID. Every transaction in Postgres has a number associated with it, a unique number. And these are incrementing numbers starting at 1 and going up. And so this is just transaction ID 99 for an example. And over here, this xmin, this is the minimum transaction ID that is able to see whatever value has been inserted over here. At the insertion step, we put the 99 here in the txmin, just 99 right here. And then in txmax, we have a 0 over here, all this other 0, 0, 0, 1. This indicates that this is just the current transaction that is able to view this transaction ID. This 0 for the txmax is a special value saying that this is the current value, that this transaction is still ongoing and no other transactions besides 99 are able to see this transaction, are able to see this value. When we eventually get to this commit over here, the txmin will stay at 99. The txmax over here get updated to a 1 value, and then every transaction that has a transaction ID greater than 99 will be able to see this transaction or be able to see this inserted value over here. Next picture over here is, I'll scroll down. Deletion, the way deletion works is that if I need to delete a value, say in transaction ID 111 right here, what's going to happen is that we will update this txmax with the transaction ID that we're currently inside of. And so no transaction that has a transaction ID larger than 111 will be able to see the data that was deleted right here. And only transactions whose transaction ID is between 100 and 111 will be able to see that data. The important piece of information here is that whenever you run the delete command from Postgres and pSQL and Python on a SQL database, whenever you run this delete command, you're not actually deleting data. You're just updating a value somewhere in this header information on that particular row. And that should hopefully make sense that you can't actually physically delete it at that point because other transactions need to be able to potentially access it. The last part here about updates. At a high level, an update is just an insert, or sorry, a delete followed by an insert. You can see over here, we don't need to go into the super detailed examples, but this tcid and tctid values also do get updated when we call an update. So an update's like an delete followed by an insert plus some extra potential modifications. The key thing about an update, though, we're not actually ever updating the user data. This user data section will never change once it's been inserted. All we're doing is we are changing some of this metadata to indicate which rows are visible or not visible to different transactions. The super high-level overview of this, what's going on when we do the insert delete updates. Again, the main takeaway, updates, deletes don't actually modify any data that's sitting on the hard drive. it just updates this meta information and potentially adds new rows. Okay. Let's see, that we already talked about. We'll do this one at the end. Okay, vacuuming. So vacuuming is related to this inserting, updating, and handling some of the edge cases or some of the weird behavior that were as a consequence of the way that insert, update, and delete work. We have seen the vacuum command in your previous quizzes where you were responsible for figuring out what kind of locks were being acquired, but we haven't talked about what vacuuming actually does. And so that's what we're going to do now. There's two types of vacuums: the concurrent vacuum, which is also just called a vacuum. So concurrent vacuum and vacuum are the same thing, and then a full vacuum, which is different. Okay, so we're back to this picture over here on the left-hand side in green. This is the actual representing the physical data stored on the hard drive in a collection of pages, one right after the other, inside of a file. And then these sort of zoomed in, blown up sections are just one of these individual pages inside of it. And what you'll see right here is that we have this tuple 1, tuple 2, tuple 3. There's this thing called a dead tuple right here. A dead tuple is a tuple that's no longer visible to any transaction. And so how can that happen? Well, we saw before from our delete command right here, the delete command doesn't actually delete information from the hard drive. It just updates this txmax variable inside of the row header information. And so the maximum transaction ID that can view this delete operation is 111. And as soon as all the transactions below number 111 have terminated, have committed, or aborted, then there is no other way, no existing transactions that will be able to see this user data right here, because no other transaction will have a transaction ID less than 111. So we call this a dead tuple after no other transaction is able to view it. So this dead tuple 2 right here, it has been either deleted or updated from a transaction, and then all previous transactions have closed down, committed, or aborted. So there is no way logically for any transaction, any session, to be able to see this information right here. That's what a dead tuple is. Dead tuples are one of the concepts that's going to come up and be important inside of indexes. When we do a vacuum, the high-level, big picture idea of what a vacuum is, why we care about a vacuum, is that it removes those dead tuples. And actually, I want to say that it frees up disk space. We'll see that that's not quite the right way to phrase it, but the intuition here is that it's going to free up some disk space for us. The more technically correct thing to say is that it's going to make the hole here larger. It's going to make the available space, the unused space, larger right here. By freeing up this tuple, we'll now have more space inside of this hole in order to add new tuples without creating a new page. But again, when we run that delete command, we don't actually reduce the size of our files on the hard drive, because the size of our files on the hard drive is always just the number of pages that we have times 8192. And we don't actually reduce the size of our space in the free space here. We don't increase the size of our hole because we're just marking this as dead, just changing the transaction ID when we delete it or update it. The vacuum process is what goes through and actually deletes these dead tuples, giving us more space here to work with. Yes, Ron?
All the tuples left in that page are dead tuples, just vacuuming delete the page.
This is a great question. So the question is, what happens when all of the tuples in a page are dead and the vacuum process goes through? What is it going to do? It's going to delete all of those tuples, but it will not actually free up any disk space for us. Vacuum process by itself never deletes a page. By default, tables in Postgres can only grow in size on the hard drive. As we're inserting new tuples, if we fill up all of the pages, then we have to create a new page. And by default, Postgres will never shrink that table for us. It will never delete a page. If we do want to delete a page, then what we have to do is the full vacuum procedure. The full vacuum will actually free up some space for us. Okay, good question. One next thing to notice over here is that when we do this vacuum procedure, so previously we had 3 of these line pointers, 1, 2, and 3, pointing to our tuple 1, 2, and 3 inside of this page. After we perform this vacuum procedure, we still have 3 line pointers, 1, 2, and 3 right here. So we don't get rid of this line pointer number 2 right here. We just change where the other line pointers are directed to. That, again, will be important for our indexes and that they are able to maintain correctness, finding the information. Okay. How does vacuum work efficiently? Or why does vacuum not delete pages? Another way of thinking about this is that we want our vacuum process to be something that can run concurrently with many other processes on the database, that these updates, deletes are going to be happening all the time. We want to be removing those dead tuples on a regular basis. And so in Postgres, there's a process called auto vacuum, which runs the vacuum for us continuously and is removing these dead tuples. In order to make the auto vacuum efficient, there is another file called the visibility map associated with each table. And the visibility map is just a bit array of 1s and 0s. So 0, 1, 0, and so forth. And so the visibility map will take up basically no space on the hard drive compared to the actual heap table over here, which is 8192 bytes per page. The visibility map is 1 bit per page. And this bit just indicates whether there is a dead tuple or not. If there's a 0 inside of here, then there's a dead tuple. If there's a 1 in the visibility map, there's no dead tuple. As the vacuum process goes through here, it will lock each individual page one at a time. If it has a 0 in the visibility map, it'll lock that page. And so reads, writes, updates not allowed to any tuples that happen to be sitting inside of that page. This will be a very short-term lock. The processing here is very efficient. So usually the end users don't observe that lock happened. But again, when we're creating indexes, that can sometimes cause problems for us. And the vacuum process continually just big for loop over this visibility map. Every time it sees a 0, locks that page and deletes those tuples. It's important, again, that this is happening on a page-by-page basis so that we don't have to lock the entire table to do this. We only have to lock one page at a time. And then if somebody's waiting on that one page lock, this processing the page takes just a millisecond or so. And so that lock will get released very, very quickly, and they'll be able to get access to the data very quickly. So the takeaway here, the vacuum process happening on a page-by-page basis for efficiency reasons. The full vacuum, on the other hand, is different. So here, this picture is illustrating a worst-case scenario for the regular vacuum process. On the left-hand side, I have, the picture has 3 different pages listed, and you can see in each one of these pages, it is totally full of data. There's no room for any information to be added to any of these pages because of all of these dead tuples. Each one of these pages has one live tuple, the blue tuple over here. It's visible to currently running transactions, so we call it a live tuple. And these slashed out tuples over here, they're dead tuples. And so if we were to, at this point, we have 3 pages right here. If we were to try to insert a new value or to update one of these values, then we would have to create a new page in the table, increasing the amount of disk space used. If we were to run vacuum on this, so this is again the concurrent vacuum or the normal vacuum process. If we're running this concurrent vacuum process, then what's going to happen is page by page, we will remove all of these dead tuples, and on the right-hand side is what the final result looks like. This is definitely better than on the left-hand side, because now on the right-hand side, if I do want to insert a new tuple, I have lots of free space here that I can insert the tuple into directly without having to create a new page. So the vacuum does help us a lot, but notice that it doesn't actually reduce the amount of disk usage used. These 3 tuples, they could, in theory, fit into a single page, and we could reduce that, the disk space usage. We could reduce the disk usage using the full vacuum, but the regular vacuum will not reduce the disk usage. It'll just delete those dead tuples.
You may have said this, but just to be clear, this vacuuming, all it's doing, is it just updating the header bitmap, or is it like actually overriding the values?
Yeah, so getting a little bit more mechanically about what the vacuum process is doing is, so the first thing the vacuum process will do is it will acquire a lock on the particular page inside of the table so that nobody else is allowed to read, write, or update to any of these tuples. It doesn't block the entire table, but it does block the page. And again, it's only for like less than a millisecond, so it's a strong lock, but it doesn't actually impact performance. And then what information actually gets updated by the vacuum? There's 3 pieces of information. The first and most important is that down here, this dead tuple is removed, and so it will shuffle around the locations of these other tuples on the disk. And say like tuple 1 right here, this is not moved at all because we are deleting something that happens after tuple 1. Tuple 3, though, that does physically get deleted from where it's currently located and then rewritten into a new location right here. In order to rewrite tuple 3 right here to a new location, we also have to adjust the line pointer right here. We also adjust part 3 of this line pointer here. And there was one other pointer that's not displayed in here in the header information up here called PD upper, which shows the upper and lower bounds of the whole free space. That information will also get updated. So the vacuum process does touch and rewrite basically every piece of information in the page here. For efficiency reasons, how it's actually implemented is it rewrites all 8192 bytes to the hard drive, all 8 kilobytes to the hard drive as one block, because hard drives, turns out that so the reason why this size right here is 8192 and not something else is because physically the way hard drives work is you cannot write less than 8192 bytes to a hard drive at once. So Postgres actually recreates this entire piece of data in RAM and then sends off to a low-level system call that writes all of this at once to the hard drive. I don't know if that's answering your question.
Okay.
Good question. Any other questions so far? Again, big takeaways of the vacuum are it doesn't actually free up disk space. It's called the concurrent vacuum because it operates only on one page at a time, and so it doesn't have any strong locks on the table. But it does have a strong lock on the page, but the page lock lasts a very short amount of time, and so those page locks are essentially transparent to the user. Another property is these page locks can never deadlock. Page locks will never deadlock. Okay, so sometimes we might want to actually free up disk space. If we're in this situation here on the right-hand side where we have a lot of pages with empty holes inside of them, then we might want to actually free up disk space. And that is what the full vacuum does. So the full vacuum, there's a picture describing what the full vacuum does. The full vacuum first takes the strongest possible lock out on the table, the exclusive mode lock. There was one that was just stronger than the exclusive mode lock, though, the name's escaping me, but it's the strongest lock possible on a table. And what it does is it starts by creating a new table file totally from scratch, and then copies all of the information from the pages in the old file one at a time into the new table file. And by doing that, it is able to use the smallest number of pages possible to store the resulting information and deletes all of these dead tuples at the same time. So the full vacuum will actually save space, but we don't want to be running this all the time because nobody else can access the database while we're doing this. Nobody else can access the table while we're doing this. There are some websites that have, say, like scheduled downtime maintenance, say like at 3 a.m. every Sunday, something like that. The reason for these scheduled downtimes, scheduled maintenance, is so that a full vacuum process can be run when nobody else is using the table. They just bring the whole web page down temporarily so that this process can run and nobody is expecting to be able to use the table. These days, because hard disk space is so cheap, it's fairly rare to have a website with scheduled maintenance like this, and most CTOs, most administrators of a database would prefer to just buy more hard drives and stick them in the server and waste a bunch of disk space rather than have some downtime. So the full vacuum, a relatively rare thing to do these days. Any questions about that? Max?
Besides other people not being able to access tables during the full vacuum, what other errors or issues could happen when doing something like this, like in the real world setting?
So let's see. So one of the things about Postgres is, and I've mentioned this a couple times, is that Postgres takes data integrity extremely seriously. And so there are test cases that Postgres runs where they put a bunch of trash data into a database, run a whole bunch of updates and deletes on that database, and then they start the vacuum process. And then somebody comes along with a hammer and smashes the computer. And that is literally part of their like test process, is physical destruction of computer hardware. And they have not detected any faults in their system, even under like hardware faults like that. There are other database systems. So in SQLite, for example, SQLite is, in order to maintain portability of the database, it tries to make sure that everything is always inside of one file at a time. And so they have a similar full vacuum procedure where they try to keep everything in the same file at once. Nobody knows about any existing bugs in SQLite from doing that, but if it's much more likely that the data gets corrupted by keeping things in the same file and trying to update that file at once. If somehow like the database actually got corrupted while doing this full vacuum procedure, because everything's in an entirely new file, we can just roll back to the previous file that we haven't actually modified in any way. So the only downside here of the full vacuum, and it's a serious downside, is that it has a very strict lock on the table and nobody else can use it while full vacuum is going on. If you have a table that's, say, like a terabyte in size, so on the order of the Twitter assignments that like you're storing all of the tweets from the last 5 years, a full vacuum process, I would expect it to take probably multiple days to run. So it's a very slow command doing all of this. But I would not expect ever to have data integrity issues or anything along those lines. Any other questions so far? All good questions. Okay. Vacuuming does one other thing too that's very important and related to this complicated looking picture up here. So what is this picture? What this picture is illustrating is something called the transaction ID wraparound problem in Postgres. And this is a famous limitation of Postgres that other databases don't have for various reasons. But let's come back to this picture right here about what happens when I do an insertion. So I mentioned that this txmin variable right here, this is a 4-byte number. And 4-byte numbers, 32 bits, can store relatively large numbers up to 4-ish billion in size. A 32-bit number can store about 4 billion numbers. And so in Postgres, you can have about 4 billion transactions going on at once. And that sounds like a lot of transactions, but if you are, say, Instagram, where your goal is to have every person in the country, in the universe, in the world on Instagram having their own separate accounts, that means that you would not be able to have every person having a transaction at the same time because there are more than 4 billion people in the world. And even at systems much smaller than Instagram, we end up running out of transactions fairly frequently. So 4 billion sounds like a lot of potential transactions, but in practice, it's actually not very many transactions at all. And the way that Postgres handles this is what they call transaction ID wraparound. So here, in our previous example, insert example, we were in transaction ID 99 when we were doing the insert. And so all of these transactions, let's see how they did it. So here, this number right here, 231 plus 100, so 2 to the 31. This is exactly halfway point in the 4 billion numbers out of the 2 to the 32 bits. 2 to the 31 is just setting the very first bit here to 1. And so all of the transactions that have our previous, like half of that action space is set as visible, and the next half, everything future of that is set as invisible. But notice that this is wrapping around 0 right here, and so the future includes transactions that are actually have a number larger than us, have a transaction ID larger than us, and the future also includes numbers over here that has a transaction ID that is smaller than us, because it wraps around going to the point where it is exactly 2 to the 31 away. And so this number 100 is considered visible, but 99 considered not visible. In order to know what the current set of minimum transactions are, where this number is lined up at, the vacuum procedure, one of the things that it does as it scours through the tables over here is it keeps tracks of, for visible tuples, what is the smallest transaction ID that is still relevant, and updates this sort of weird circle right here to so that it knows where the visible and invisible transaction line is with this wraparound past 0. The exact math over here, not super important. So the key takeaway here is that because this transaction ID number txmin here is 4 bytes, we only have 4 billion transaction numbers that we're allowed to work with. And half of those, 2 billion of those, will be considered visible. The other 2 billion considered invisible as being in the future and the past. And vacuuming is important to do in order to make sure that we have as many visible and invisible transactions as possible. If we don't vacuum regularly, then we're not updating this information about where the visible and invisible transactions are, and we will run out of transactions. One of the ways this comes up is that occasionally for large databases, it is the case that you cannot create an index or cannot do certain operations on your tables that you would like to do because a vacuum is currently in process. And one of the temptations of beginning data engineers is to disable auto vacuum, disable vacuuming on tables. This is a temporary solution that allows you to immediately do what you want to have happen, but it will result in you running out of transactions very quickly, and then your website will be down for a long time if you run out of transactions, because you won't be able to do anything until auto vacuum is re-enabled. And if it's been taking a long time, or if it has not been recently, if you have not run vacuum recently, vacuum will take longer to do. Coming back here, that visibility map, one of the reasons we have this visibility map is to speed up the vacuum process. If the auto vacuum is running regularly, then usually there's only one or two of these pages that have dead tuples inside of them, and so it goes very quickly. But if we stop running our auto vacuum process, then many of these pages will have dead tuples inside of them, and so vacuuming will take a long time to run. Again, on a typical database with, say, a terabyte of data, I would expect multiple days to a week to have the vacuum process run from scratch. Any questions about any of that?
Yeah, how do the circles actually get around the, like, having 4 billion concurrent users problem?
So we cannot have more than 4 billion concurrent transactions. What we can have, though, is 4 billion. Let's see. Yeah. So actually, we have this limit of 2 billion concurrent transactions at once that could be happening where they're all visible to each other, and that's just a hard limit. What the wraparound allows us to do is to have, like, once we've used this transaction here, once transaction 100 right here is no longer used by any possible transaction, then the vacuum updates this line and makes 100 usable again for a future transaction. So this wrapping around of the transaction IDs allows us to have an infinite number of total sequential transactions, but still only 2 billion concurrent at once.
Does anybody like really need to solve that problem of having 2 billion concurrent transactions, or?
If there were, it would be Instagram, and they have not made an attempt to solve that problem. Technically, it's not hard to solve that problem. All you have to do is update all of the code to change this from a 4-bit number to from a 4-byte number to an 8-byte number everywhere, which ends up wasting a little bit more disk space, and it's would just be obnoxious to do, to update all that code, is why nobody's done it. But technically, it's not a hard thing to do. It's just update these values from 4 bytes to 8 bytes, and then everything will work. And you could have, 8 bytes is a very large number of total transactions and concurrent transactions. Good question. Any other questions? Okay, we went through this material pretty fast today, and I don't have anything else that I want to talk about it. Again, you're not responsible for reproducing any of these plots for me. We will be responsible for understanding how these indexes work. We'll talk about that starting next class period after our quiz. And in order to understand the indexes, you do especially understand the format of these pages down here, and how there's these line pointers right here pointing to tuples in the page. Understanding how there's dead tuples and that vacuum removes those tuples, that the update delete commands don't actually update or delete information from the tables. All they do is mark it for future removal by the vacuum process. Those are the key takeaways from today's class. Next time we'll get into the actual indexes, but we'll end today 20 minutes early. If anybody has more questions about anything, homework or this or anything at all, stick around and get those answered. Otherwise, enjoy the rest of your morning and see you on Thursday. Go.
Is the quiz on Thursday just the section of the factor we have? Or just
Everything, including review. Yeah. Hey.